Wo landen diese Sachen? Wo landen diese Instrumente? Was wird daraus?
Okay, I guess I'm supposed to be starting now. Sorry, I was waiting for some cue, but actually I see it says I'm in the show, so I'll start talking. Hopefully I'm supposed to. So welcome everyone. I assume I was introduced, but I couldn't hear anything that was going on. I am Ryan Henry. I'm an assistant professor in computer science at the university, as well as the director of our Master's Information Security and Privacy program. Many of you have probably taken classes with me and know a bit about me, but for those that don't, I do mostly privacy-focused cryptography research. And so the talk that I'm going to give today is about some fairly cutting-edge published with a former student and my former PhD advisor, coincidentally. So three generations of academics, I guess. So the scheme was called Duoram, and the subtitle I've chosen for this is MPC-friendly ORAM with impossibly low communication. So I'll explain what this all means before we get into things. So to begin with, this term ORAM, you're probably not familiar with. This just stands for Oblivious RAM, where RAM is what you are familiar with, random access memory. What exactly this means, we'll come to, but the term ORAM just means Oblivious RAM. The particular type of ORAM that we're talking about is MPC-friendly. What this means is that it is suitable for use in a type of protocol called a multi-party computation protocol, which we'll come back to exactly what that means as well as the talk progresses. But just to give you a bit of context as to where this belongs. So this is specifically looking at relatively small numbers of parties, which tends to be a place where it's hard to get the sort of efficiency that we've got here. So for a 4-party protocol, we have a construction that is surprisingly efficient. When you move to the 3-party, it's kind of like shocking that we can get things as efficient as we got them. And for a 2-party protocol, I sometimes have to pinch myself to make sure I'm not sleeping, because I have kind of gone my whole career assuming this sort of thing was impossible, like many cryptographers. But here we are. And so like I said just a moment ago, this is kind of a surprising result in that the communication cost of the protocol that we've come up with is so low that most people would just claim or assume that it's impossible. And in fact, I thought it was impossible as well. And it was a realization that the impossibility result doesn't quite perfectly apply here that ended up leading to a construction that does significantly better than the impossibility result that would make you think this is impossible seems to imply. And so in particular, we've gone from big O of square root n, for those of you that know your big O notation in it. For those that don't, this is just big O means as numbers get big, the growth of the communication cost kind of grows like the square root of how big your database is. And we've turned that into something that is constant. So huge improvement in practice. And yeah, and there's other metrics, and we'll come back to this. So that's the title, Duoram, MPC-friendly ORAM with a impossibly low communication. Hopefully that whole thing makes sense at this point. So let's get into it. So ORAM has a long and storied history. The first ORAM protocol was proposed back in 1987. What that protocol was intended to do was allow you to either outsource data to some other party. This was long before the word cloud was a thing, but you can think of this like putting your data out on the cloud, and you want to be able to then access that data without revealing to the cloud or to whoever's hosting it for you anything about what you're doing at the time. And so in particular, it's trying to hide which of the data that I've outsourced to it I'm actually reading. And if I go to write data, the cloud shouldn't be able to figure out which of the data that I'm storing that I've written over. So I can read data, I can change data, and it even goes a step further and says, when I interact with my data, obviously the cloud knows that I've connected and done something, but we don't even want to reveal to the cloud whether this was a read or a write, let alone which part of the data was read or written. And so the original schemes had the square root complexity that I said that we've improved upon in this protocol. Somewhere around the 2000s, people came up with these really clever constructions where the user had to store certain data on their side called a stash, and with the help of the stash, they could get the computation and communication costs both down from square root to logarithmic, which is really great. These protocols are quite efficient in practice, but they are very specifically single client protocols. They maintain state at the client, and if anyone ever learns that state, then they can learn all of the things that the ORAM is designed to protect. So they would know what you've done in the past based on the state. Fast forward a little bit, in the 2010s, people started getting really interested in this thing that I mentioned, multi-party computation, which I actually started to become summarized, was about to go mainstream and was going to be seeing deployment. And so they started looking at how can we put ORAM protocols in multi-party computation. I'll explain what the super short version of this is. If you're doing a computation in multi-party computation and you want something that plays the role of RAM, then you either need to do something really that in your computation cost. And that was sort of the state of the art up until this paper, where we took the communication cost and turned it from a square root cost up to a constant cost. And if we were to extrapolate from here, looking at this sort of progress, I'm just guessing, nobody knows, but my guess is that by like 2030s, it'll be cheaper than free, because we've taken such a big, no, I guess cheaper than free doesn't make sense, but things have gotten much, much, much better. Probably we're going to see some deployments of interesting MPC protocols using ORAM protocols similar to the one I've. So while we're, let me go back in history one more time, this time to Dallas in the year 2017. So I was presenting some research at the conference CCS 2017 in Dallas. I ran into Ray Safavi Naini, who at the time was just a fellow researcher that I knew from being fellow researchers. Now she's a dear colleague of mine. And Ray told me Calgary was hiring in security. I wasn't even looking for a job at the time, but I thought, hey, I'd like to go to Calgary. Manitoba boy, I wanted to go back to the prairies. So I applied, and here I am. The other thing that happened at that conference was Jack Dorner and Abby Shalott won the best paper award for their protocol FlowRAM. And so actually, if I go back to this, the 2010s here, where I said the stateless distributed client protocols first came out, that this was actually FlowRAM was the first of those. And so it was a really, really slick construction. Obviously, it was well received, and possibly tried to publish it at. And what it is it's like what I'm talking about today, an MPC-friendly distributed ORAM protocol. It's very fast when the memory that you're trying to represent with it is reasonably small, and concretely blew everything that existed before out of the water. And it used a variety of techniques that were near and dear to my heart. I was actually at CCS talking about PIR, private information retrieval. I gave both a research talk and a tutorial on PIR that year. PIR writing, which is very closely related to PIR, just PIR is for reading, PIR writing is for writing. Something called garbled circuits, which I was not presenting there, but something that's super cool that I'll talk a little bit about, and something called distributed point functions, which I was just starting to pay attention to and have done an ungodly amount of research on. Writing code for my distributed library. So obviously impossible, and then I stopped thinking about it. Oh, right. So let me just my opinion of their paper, my critique of their paper, whatever you want to call it. It's some awesome cryptographic engineering. They have some ideas, but they didn't actually break any barriers. And when I was thinking about how to improve on their thing, I was really thinking, oh, here's an idea to break a barrier and to do something like fundamentally new. But then, as I mentioned, quick to do was clearly impossible, and I should quit wasting my time trying to do things that I know to be impossible. So what is the impossible thing? So there's a handful of impossibility results that underlie what they have done in that FlowRAM paper. The first one is they have a linear computation cost because the scheme is based on PIR, and there is an impossibility result that says you can't do PIR with a sublinear communication cost. So basically, what PIR is the reading part of ORAM. You want to be able to read. And the super informal argument for this proof is that if you don't touch some bit of the database while answering a query, then clearly the user can't learn that bit of the database. Thus, if you want to make it so that all bits of the database are to include every single one of those bits as an input and have a cost proportional to how many bits there are. So there's another impossibility result that basically says for PIR writing, same thing. If I want to write one entry of a database, but I don't want you to know which one, I need to change every bit of the database somehow so that you can't tell which bits were unwritten, and then infer that I couldn't have possibly written there based on that. And impossibility result number 3 essentially says that if I use PIR writing to write to a distributed database, and then I try to use PIR reading to read from it, this one's a major showstopper because linear work is then okay, but linear communication is super expensive when you're talking over the internet, right? To do a loop over a megabyte of stuff in RAM takes approximately 0 microseconds. It's almost instant. But to send a megabyte over the internet takes hundreds of milliseconds just in latency. If we start looking at a gigabyte, doing a loop over a gigabyte of data might take you tens of milliseconds. But to send that gigabyte over the internet, well, a gig is a fairly large amount to send. It takes a noticeable amount of time, and things just keep getting worse and worse as you make the memory bigger. So these are sort of the limitations that they had to live with when constructing their protocol, and just accepted. So it turns out that these are all what are called folk theorems. They are something where if you were to probe cryptographers who really know what they're talking about, pretty much every of them probably couldn't tell you where it's been proven or if it's actually been formally proven. Turns out the first one has. It's just not something everybody knows. It was actually in the original PIR paper they had the proof of this, and it's been proven a few times since, but still it's usually stated without proof, and most people probably couldn't tell you where to find a proof. The PIR writing result, similar state of affairs. It was in the first ever paper on the topic, but most people just know it's true without having ever seen anything like a proof or knowing for sure whether a proof has been written down. And then the third one was never really proven anywhere. It's just a very obvious corollary to a theorem that does have a proof, which I'll come back to. Okay, before that, we're going to talk about rich people bragging about how rich they are to motivate multi-party computation. So if we go back again in history, this one is now late 70s, like 78 or 79, if I remember correctly. A very smart fella named Andy Yao came up with a neat construction to solve what he calls the millionaire's problem. So we have Alice and Bob here. Alice and Bob are two very, very rich people, and they are very private people. And so they're having a disagreement about which one of them is richer, but because they're both privacy conscious, neither one of them is actually willing to divulge any sort of real indication of their net worth to one another. But yet they somehow want to figure out which one of them is actually richer. And so Andy Yao proposed a really clever solution to this problem. So the question is which one of them is wealthier, and that the solution that he proposed is what actually his first solution was different. But a few months after he posted his first solution, he came up with a second solution, which is now what we call garbled circuits. So I'm going to talk about garbled circuits in a minute, but basically what garbled circuits accomplish is, imagine we have some sort of magical black box. This is magical. It does things that are clearly impossible to do, and it just does them, and it never fails because it's magic, or it's just a thought experiment. We call this an ideal functionality. So what MPC lets you do is define these ideal functionalities that accomplish some specific thing, and then build cryptographic protocols which mimic the ideal functionality in such a way that it accomplishes the same thing as the ideal function. It's using crypto, and if you can learn anything from it that you wouldn't be able to, logical thing, which by definition leaks anything, this magic box does is it lets both parties enter their net worth into the black box, and then it just spits out the answer of who's richer without giving any indication as to like what the actual net worths were. So if you think about this, if Alice learns she's richer than Bob, she knows how much she reported she's worth. So she learns that Bob must be worth less than that, but she learns nothing more about how much Bob might be worth other than it's less than. He learns that Alice is richer, so he knows that whatever Alice's worth is must be higher, bigger than mine. But he learns the answer, and you learn absolutely nothing except for your own input and what you can infer from the answer. And yeah, it was richer, but that was sort of the original problem and a very easy one to conceptualize. And so Andy Yao's solution to this is something called garbled circuits. I don't actually use garbled circuits, but they're so cool, I thought I would give you a little bit of a flavor as to what they are. Our scheme does something slightly different than garbled circuits, but you guys are presumably all familiar with digital logic circuits. Maybe you don't know too much about them, but you know they exist. You have a bunch of different types of logic gates. You string them together with wires, you feed some voltage through them, and boom, you've got digital electronics that can do all kinds of stuff like computers or simple locks. And this idea that and uses it to implement arbitrary computation. So it's a neat idea. And the way it works here, we have Alice and we have Bob, and they agree on a circuit that would come up to a comparison circuit, but if they were doing the put in the two numbers, and it would compare them and spit out a one-bit answer saying the first number is bigger or the second number is bigger. So once they've agreed in principle on what circuit will produce the answer they're looking for, then one of them gets designated to be something called a garbler, and one of them gets designated to be the evaluator, and then they work together to actually learn the answer to their problem. So basically the garbler, in this case Bob, takes that circuit and does some weird crypto stuff to it to produce what's called a garbled version of the circuit, and sends it over to Alice. And then Alice and Bob interact with one another using something called oblivious transfer, which I'm not really going to talk about, but I'll give you the sort of the plain English description of what it does. Oblivious transfer allows Alice to go to Bob and fetch one of two values from, so Bob has two values, Alice gets to fetch one of those two values. And the security guarantees are that Bob learns nothing about which of the two Alice fetched, and Alice learns nothing about, she may ask, she'll get it, but she won't learn anything at all about the second value. Or if she asks for the second value, she'll get that, and she won't learn anything about the first. And poor Bob has no idea what she learned. All he knows is that she learned one or the other, and definitely not something about. She figured out how to put inputs into the circuit, and then she goes ahead and evaluates it, and then she gets answers which she can't understand, and she sends them to Bob, and then Bob says, oh, here's what those answers mean. He can't figure out what Alice's input. So what does this garbling process do? It's kind of a neat construction. It's tangential to what I'm talking about, but it's cool enough that I felt like I would talk about it anyways. So you've hopefully all seen truth tables. This is the truth table wire here and the B wire. Each of those wires can take on two different values, either 0 or a 1, a high voltage, low voltage, true, false, whatever you want to call it. And based on those two answers, the output wire of this gate will take on 0 or 1, high or low, true or false. And so in this particular case, if either one of the input wires is 0, then the output wire will be 0. And if both input wires are 1, the output wire will be 1. And so to garble this gate, the process is, at first it seems weird and arbitrary, but you'll see how it all fits together nicely at the end. So we start by taking that truth table and just replacing all the 0s and 1s with something different. So in particular, on the first wire, the one that I've labeled A, we choose a random value that's completely random, has nothing to do with anything. When you look at it, it just looks like random garbage. Call it A0. And we say instead of the input being a 0, anywhere where the input should have been a 0, we're going to put A0 in instead. And then we do the same thing for the one wire. So now you have two random values. And by looking at these values, you have no good way of saying whether this value stands for 0 or 1 because they're just random. But if we do the same thing for the B wire, so a different random value for the 0s on the B wire and a different random value for the 1s on the B1. You can't figure out whether this is supposed to mean 0 or 1, but if you were the person that created this table, then you of course know what it means. And then likewise for the output wire, we do the same thing. We say if the output is 0, we're instead going to output C0, which is just a random thing. And if the output is 1, we're going to output C1, which is again random. So again, if you see the output, you can't tell whether this means 0 or 1. And then we're going to do something kind of clever. So we take those output wires and we encrypt them twice. So the first one here, we've taken C0. I'll come back to why this 0 to the n is there after, but you could ignore it for now. We take this C0, the 0 output, and we encrypt it using B0 as a key. And then we take the result of that encryption and we encrypt it again using A0. If I know A0 both, I can learn C0. If I don't know A0 or I don't know B0, there's just no hope of me ever decrypting both of these correctly and learning C0. And the reason that those 0s are at the end is because C0 looks completely random and there's no way to distinguish a failed decryption that produced a random result from a successful decryption, which produced a random result. So we throw these 0s at the end. And now if I decrypt it and I get something random followed by a whole lot of 0s, I know that my decryption succeeded. And if I get something that's purely random without all the 0s, I know that this is just a completely random thing because my decryption failed. So we do the same thing for each row of this table. So the second we encrypt C0 again, the same value for the output because this row of the real truth table has 0s. We encrypt it under B1 and then A0. We encrypt it under B0 and then A1. And then we take the value that stands for 1 and we encrypt it under B1 and A1. So now, if I give you A0, B1, for example, you can decrypt one of these ciphertexts and only one of these ciphertexts and learn the output label on that garbled gate, right? And then once you have that, you could use it as the input to some other gate. Of course, so far, this all seems very silly. If I gave you this truth table and said, you know, what does it encode? And if I give you a couple of inputs, I say, guess what these inputs are? You can tell just by looking at the layout of the table. So from here, the next step is we permute it randomly so that the particular row you happen to be looking at has nothing to do with anything. And you can't just and then we only show you the encryptions. So now you just have 4 encryptions. They're in a random order. But you do know that if you learn A1, B0, for example, you can decrypt one of them. So you try to decrypt all 4, only one of them will yield all of the 0s, and then you know that was the right one, and then you know what C0 was in this particular example. Or maybe you got A1, B1, so you'll try to decrypt them all, only one of them will end with a bunch of 0s. So based on that, you'll know that this is the output C1, but you don't know whether that stands for 0 or 1 unless you knew what the input label stood for. And then in order to build circuits out of this, you just string these things together. And you can do arbitrary digital logic circuits this way. So as you can see, it's a clever construction. It's also going to be kind of expensive if you have to take every single logic gate in a circuit and represent it with a whole bunch of encryption. It's going to take a long time to do, but you can do it. So there's another related thing called additive secret. How does additive secret? Suppose you've got a secret. In this case, I'm going to call it A, and I want to share it amongst multiple parties so that these different parties don't know the secret. So this should sort of ring a bell with the last stuff. We want to split things amongst people, and we don't want them to be able to learn anything. But between square bracket notation to indicate shared the value A. And the way that the sharing works is we choose one of these shares completely at random, and then we make the other one, we just sort of compute the other one. So say the first one is random, the second one is A minus that random thing. So when you add the mod, a prime, or in an appropriate mathematical setting, there's a very simple mathematical proof that says given one of these, only one of the two, it's literally impossible to learn anything about what the secret was. But as soon as you have both of them, you just add them together and boom, the secret pops out. So that's kind of nice. And it has some nice properties because we're just doing addition. So if I have two secrets, say A and B, and I've shared them both, you can just add the shares together and you've come up with shares of A plus B. So I can do some basic computation this way. If you multiply them by scalars, similarly, everything works. So I can take arbitrary linear combinations, and essentially anything that you do in linear algebra is very easy to pull off in this secret sharing setting. So if you have particular computations you want to do where everything is linear, it's super trivial to do here. And if you have computations that you want to do where everything is naturally expressed as a digital logic circuit, it's particularly easy to do here. Okay. I'm getting somewhere with this. It also turns out that you can multiply shares together. It's more complicated and it looks intimidating, but I want to give you a feel for it because this is actually key to the breakthrough behind the Duoram protocol that I'm getting to. Sharing a share of A times B when all I have is a share of A and a share of B. So we have these two secrets. They've been split between two parties so that neither party knows them. And now we want to come up with shares of their product. Before we came up with shares of their sum and saw that's super easy. Shares of their product is a little bit less easy, but still doable. So the first step for that is we just say, okay, if we were to take A0 and A1, add them together, we would get A. And if we took B0 and B1 and added them together, we would get B. And if we multiplied A and B together and then we shared that, that would give us the answer we want. The problem is that whoever actually did this would learn both A and B and A times B, and we were trying to avoid revealing our secrets to anybody. So we're not happy with this solution, but it would, of course, work to get the right answer. Then we just apply some high school level algebra, the FOIL rule. So we look at all of the different terms that you get when you expand this out, A0 times B0, A1 times B0, A0 B1, A1 B. That's the same as this, which is the same as this. So that would give us. Then we look at this and we realize, oh, this maybe helps a little bit because Alice can compute half of this, a quarter of this all by herself. She knows A0 and B0, and that term A0 times B0 shows up in the sum. And Bob can compute a quarter of it as well because he knows A1, B1. We just have these other two pesky terms that we're not quite sure what to do with. So if we could figure out how to multiply Alice's A0 times Bob's B1, then we would, that would also tell us how to multiply Alice's A1 times Bob's B0. If we could do that, we could compute the entire product that we're looking for, using that as sort of the key step. So I'm going to explain how we do this for just this one term, A0, B1, noting that the other one is exactly the same. So Alice has A0, Bob has B1. The way that this protocol works is pretty clever. I'm actually going to lie to you at first and come up with something that doesn't quite work so that you can see why we introduce a little slight modification to make things work. So Alice is just going to choose a random number, call it R. She's going to add R to A0 and then send it over to Bob. So now in a sense, Bob has A0 and B1, but A0 is sort of wrong because R is being added to it. And because R is random, it completely obscures from Bob what A0 was before R was added. Likewise, Bob is going to do the same thing. He's going to choose his own random value S. He's going to use it to make B1 look like random. He's going to send that to Alice. So now Alice, in some sense, has A0 and B1. And then if Alice just computes the product using B1 plus S, and then Bob uses his S and computes this thing, he takes S times A0 minus R, we see that what happens here when we try to simplify this is that the S's cancel out and we're left with the A0 B1 we wanted, but with some extra minus RS term. So somehow we need to take the random thing Alice chose and the random thing Bob chose and multiply them together in order to cancel out the RS. Choosing RS in the first place. However, there's one key difference. If this was an interactive session, this would be a time when I would force somebody in the audience to tell me what the key difference is, but I can't do that, so I'll just tell you. The key difference is that R and S are completely random. They're have nothing to do with any secrets. So, well, we can't tell Bob R because he could use that to learn A0, and we can't tell Alice S because she could use that to learn B1. R and S are otherwise not sensitive at all, and we could tell them to some other random person. So that's what we do. We introduce another third party, a very special third party here. So this third party is what we typically call a server. It's very special in that we can use a two-party protocol to actually get rid of this. So these guys can actually, between the two of them, just recreate the role of the party, and the party in some sense just makes things easier to understand. It doesn't actually have to exist, but if we are able to have it existing because it makes sense in our given use case, then it also makes things way more efficient to not have Alice and Bob just in this protocol is it chooses those random things. So it chooses R for Alice, and it says, here, Alice, use this R. And it says, here, Bob, use this S. And then it computes R times S for Alice and Bob. And then it chooses one more random value T, which it uses to they do exactly what they were doing before. Alice sends A plus R, A0 plus R, and Bob sends B1 plus S. But the difference is that when they do the product that I said before, Alice just subtracts off this R times S plus T that she learned from the server, and Bob adds the T that he learned from the server. And when you add this all together, we'll see that that extra term that we wanted to go away indeed cancels out because we have an extra we had an RS term, now we have a minus RS term. We have a new minus T term, but we also have a plus T term. They all cancel out, and boom, just the piece that we wanted survives. So that's how you multiply in additive secret sharing. So why am I telling you all of this? It turns out that just like digital logic circuits are circuits of things strung together, there's something called arithmetic circuits. I guess at first I have the digital circuits. So we have the digital circuits. I think you guys all intuitively know that digital circuits can do basically anything because everything is digital nowadays, and anything that is digital is being accomplished using digital logic circuits. And so it turns out that anything a computer can do, or anything that can be computed in principle in some very mathematically formal, rigorous way that you can actually reason about in a very mathematical way, you can prove that these are all implementable using digital logic circuits. A lesser known fact that you may find surprising, but is nonetheless true, is that if you can do addition and multiplication, you can also build circuits called arithmetic circuits that can compute literally anything that a digital circuit can do. So if you have digital logic circuits, you can do anything. And if you have arithmetic circuits, you can also do anything. And I just showed you that we can build arithmetic circuits using additive secret sharing. We can add basically for free. We can multiply. It's annoying, but it's totally doable. And as I said, in theory, all functions that can be computed by arithmetic, or that can be evaluated, can be done via arithmetic circuits and digital logic circuits. With the caveat that this is in theory. So it's true in practice, some computations are downright painful and super inefficient. There's a baby screaming upstairs. I'm sorry if you can hear that. They can be computed in theory. In practice, they may be very painful. So it turns out there are some computations that are easy to do with arithmetic circuits and painful to do with digital logic circuits. There are some computations that are easy to do with digital logic circuits and painful to do with arithmetic circuits. And there are some computations that are possible to do with both, but painful to do with both. So sometimes you want to use one of these types, sometimes you want to use the other. It really depends what you're doing. Okay. So we're finally back to Oblivious RAM. So where the heck does this Oblivious RAM thing fit into doing weird circuits and computations with arithmetic circuits and so on? It turns out that lots and lots and lots of computations access memory in such a way that the memory accesses that you make depend on secrets. So in particular, you might be doing something like a binary search. In a binary search, you start at the midpoint of your database, or of your one you're looking for. If the number is bigger than the one you're looking for, then you go left, and if it's smaller, you go right. And you as the user makes next. You can, and so if the value they're comparing is a big problem, right? We're going to be doing accesses, random accesses into memory, and if you can tell which memory we're accessing, then you can learn the secrets that we were trying to hide inside of our MPC protocol. So MPC becomes infinitely harder when you need to have RAM. All right, so we're going to go back in time again to this slide. So I mentioned here that there's these impossibility results. The first one was proven in the original PIR paper, the second one in the original PIR writing paper, and the third one is just kind of obvious. So going back to 2007, Dorner and Shalot. Dorner here is Batman. Shalot actually is he's a superhero. His superpower is that his name is always no capital letters. It's both first and last name. Antichrist, as far as I'm aware, but that's like the opposite of Christ, right? No capitals. Anyways, found this linear cost. Right? They were trying to get around the linear communication cost, not the linear computation cost. They were trying to get around this, and they did it using a clever idea. So I mentioned in the original timeline showing how PIR or how ORAM progressed over the ages, that one of the first speedups came when they started using something called a stash that maintains state on the client side and lets them get away from that square root speedup into a log size speedup. You can't really do that here. But what these two came up with was a clever idea based on a stash, which lets you only incur this linear cost from impossibility result 3, 1 out of every square root reads or writes that you have to do by using a stash in order to avoid the need to actually do the thing that requires this linear cost. So you do the thing that requires a linear cost, 1 out of every square root accesses, and in the other accesses, you're only talking to a database that is square root the size, and so it has only square root cost, and then when you add it all up, everything is a square root, and it was great. As you can see here, it saves Gotham City a full square root and factor on its communication costs, which kapow, right? And now, I mentioned that I sat through that presentation and had some great ideas and convinced myself that the great ideas clearly can't work, and that's because, again, this blasted impossibility result, number 3, the same one that they basically found a solder throw that theorem out the I say here that this is obvious. Here's another theorem. Obvious does not actually mean true. And if you want a proof of that, well, I'm not going to give it to you. The proof is obvious, but it's true that obvious does not imply true. So my idea in a nutshell is to just ignore the impossibility result, pretend it's not there, and try to build a protocol that just works. And like once you realize you can just ignore impossibility results, everything comes together very nicely. And so what is the impossibility result? Where does it come from? This showed you for multiplying things, and we want to use it to do inner products. And in that step during the multiplication protocol where you took the thing you're multiplying, you added a random value to it, and you sent it over the wire. When you're trying to do inner products, you have to do that as well, but you need to do it to the whole vector. So I take a big length n vector, I add components, and then I have to send it to my partner. So if my RAM is a gigabyte, in order to do a read from it, I do the read as an inner product. So I have to send a gigabyte of random crap to my partner, and my partner sends a gigabyte of random crap to me. And then we do a relatively cheap computation, and out pops the right answer. Everything is quite efficient, except for that step where we each sent a gigabyte of stuff to each other. That was pretty darn inefficient. And if we have to do this 1,000 times in a row, well, now you've sent a terabyte. Deal with it. And that was sort of the way things were, right? They found a way to avoid doing these inner products, which was to incur the cost. So eventually, I came up with a solution that lets us do that, and wrote a paper. Like I mentioned, Aditya here was my former PhD student, so I was Aditya's advisor, and then Ian was my advisor. So this is like a father, child, grandparent, academically speaking, authored paper that was published just this last year at the Usenix Security Symposium. So what is the secret sauce here? Well, the reason that we need to send that big, long, blinded vector over the wire to the other party is because they kind of need to have a copy of our vector. The vector to them, then we need to add random stuff to the vector to blind it. And if we try to compress things down, no matter how you slice it, it seems like we're going to be revealing some of our secrets, or the computation's not going to work. And there's even some nice information theory that tells us that that's definitely true. You definitely can't not send the whole thing without having that happen for the general case of inner products. So our idea is to be leaky, but to be strategically leaky. So you could call this our caramel secret. We want to be strategically leaky because we know that no matter what we do, we're going to leak a bunch of information if we don't send that linear stuff. But maybe we can be really strategic and make sure that the stuff that gets leaked doesn't matter at all, and the stuff that we actually care about does not get leaked. Right. So the key insight is that theorem that doesn't have a proof anywhere is true if we have n secrets per vector, which means we have 2n secrets period that need to be protected, which means we need to send like 2n values over the wire, which is showstoppically bad. But in reality, when you're looking at the RAM case, to start with, RAM is empty, right? You don't fire up your computer and find a bunch of useful data in RAM. The data gets put there as computation unfolds, and it starts off with nothing. So at the beginning, those vectors are all 0, and everybody knows they're all 0, and there is nothing to protect. It would be silly to blind zeros and send them over the wire. We just accept that it's 0 and accept that everybody knows it's 0 and leak the fact that it's 0 because everyone already knew that. Whenever a read happens, I'm saying one vector is nearly public. I'll kind of come back to exactly what I mean by that, but it's nearly public in the sense that the last time we did one of these, we got a blinded vector, and most of RAM has not changed since we got that blinded vector, because RAM is only updated, one update at a time, and we actually know how many updates have happened, so we know what has changed. That last blinded vector that we got is a blinded version of basically the same vector we still have. This new vector is almost the same. And then the other piece is, when you write something, the vector doesn't barely change at all. Every time you do a write, you change one thing at one memory address, which means that if you have like a 1 gig vector and I write a 64-bit value, well, approximately 1 gig of that vector hasn't changed. Only 64 bits have changed. It would be problematic if I reveal which 64 bits changed, or what they changed from, or what they changed to. But clearly, there's not n values to hide here. There's one value plus its location, which is very different from n. So putting this all together, everybody already knows that the memory is uninitialized. We have nothing to hide. Writes modify a single component. So every time a write happens, we have one new thing to hide. Nobody's allowed to learn where writes happened. If there's n values, that means that there's like log n bits worth of information that we need to hide. Nobody should learn what gets written. Well, if you're writing one value at a time, that's big old one amount of data per write that we need to hide for that. And when a read happens, nobody should learn where we're reading log n bits to represent which one. So the amount of data that we actually, the amount of information we actually need to hide when we're doing an access is much smaller than big O n. And so we built a construction that takes advantage of this, that actually achieves these exact costs at each step of the way. We don't know whether the constants that we have are optimal, but they're fairly small, and clearly people can't do too much better than them. But there's probably some capacity to do a little better. But in terms of asymptotics, we know that you're not going to touch what we've done here, because the impossibility result that that everyone assumed was obvious actually does apply in this case, and you can rigorously, using something called distributed point functions. I'm not really going to talk about that. I'm not going to talk about lots of the clever crypto engineering that went behind this. I just want to because I spent many hours convincing myself that there was a way to do this, and convincing myself that it was impossible, and then convincing myself that no, it's really not impossible, there's got to be a way to do it, and then convincing myself, no, you're delusional, it's impossible. And after spending so much time going back and forth, I feel like I just ought to talk about it. So here we are. So here's how the secret sauce part of Duoram works. At the beginning of the we're just going to have the vector through the protocol. So this party has a share 0 of the entire database. It's the terabyte or something big. And then R0 is the stuff that this guy would use to blind his D0 before sending it to the other party in the the less efficient version of the protocol. So he knows what his own blinding stuff is, but he doesn't ever send it over the wire. And then D1 tilde is the blinded copy of the other guy's share. So the other guy has D0 tilde, which is D0 plus R0. And this guy has D1 tilde, which is D1 plus R1. And D1 being the other share of the RAM, and R1 being the blinding factor for the other share. And then there's that other party, the server party, that has R0 and R1, but knows nothing about the actual data. It just knows the random blinds. Okay. So in the protocol, in order to do a write to the database, we are going to send a really long vector, as long as the RAM, but with all entries in the vector being a 0. We're going to submit that into the computation. So where this comes from, it could be a user inputting it, it could be the output of some part of the computation. It doesn't really matter. But when these guys are going to update, they're ultimately going to have a vector like this that comes from somewhere. And it might seem like that huge vector is going to be problematic, because if the database is like a gig, then this is like a 1 gig vector, which is huge, and we don't want to be sending these around. But it turns out, because the vector is all zeros, that thing I mentioned a few times before, distributed point functions, give you a really efficient way to represent such vectors using only logarithmic space. So this vector, because of its special form, is actually tiny, even though the representation is tiny, even though the vector is huge. And in order to make our construction work out, we also share it a second time. So these two guys, the two guys at the bottom, have shares of this really long vector that's mostly zeros. And there's another sharing of it that this guy and the server, so the Alice and the server, have this share in common, and Bob, the other value M0 to the B and M0 sub 0B are identical values, M0 or M1B. This one long vector with all zeros and a 1. And then we have another copy of the exact same vector, a third sharing server, and Bob have their share in common, and Alice has the matching share. And then from here, it's just some simple arithmetic, actually. If we update our own copy of the share using the thing that these two guys have in common, then we effectively change the value in one position from what it used to be to something new without modifying the rest of the database and without anybody learning where the change happened. And then we use the other shares to update both our blinds and our blinded copy of the other guy's database. And when you do all of this, basically everything works out almost exactly. Yeah, there's just one little piece that I've sort of swept under the rug, but Batman and Robin are already pleased here. Basically, the piece that I swept under the rug corresponding to what we actually wrote is going to be wrong, but this third party has the information necessary to fix that error, so it ends up sending something to each of these parties, and the thing that it sends is tiny. So they can fix the error without sending something that is linear in size. And boom, we have our super efficient, or I should say BAM, we have our super efficient thing. So I'm going to skip through this, but this is the proof that that stuff works out. Okay, so yeah, we can do it. The total amount of communication that gets sent across the wire there is logarithmic. I think before I said it was going to be constant, and here it's logarithmic. But in fact, we can make it constant using a little trick. So what he ends up sending is this inner product, and I'm going to skip through that. So then the trick that we use to make it constant is we move all of the part that depends on data into a pre-processing stage. So what is the outcome of this? Well, if you look at the scalability of our protocol versus FlowRAM, which was the state of the art at the time, you'll see concretely it's much slower, right? This is much slower, much lower. This is how long it takes to access memory, from memories ranging from tiny up to astronomical from an MPC perspective. We go from way faster than FlowRAM up to way faster than FlowRAM, although by this point it is taking like 200 seconds. Back here it was taking a fraction of a second. So still not fast, but compared to FlowRAM, unbelievably fast. And when we look at what happens when network conditions get poorer, we can see that if you have a very good network, we are way faster than FlowRAM. And as your network gets poorer and poorer, DORAM doesn't really notice because it barely sends any data anyways and is pretty agnostic to how much latency there is on network connections and so on. And FlowRAM just gets, whoa, that was crazy. I think I lost my screen share. I'm almost done, but I did not mean to leave the presentation there. Hold on. I don't know what actually happened. I think it was my screen that I lost. My monitor went out and killed the presentation with it. Okay. Sorry.
Are you good?
No, we're good.
Sorry.
We're good.
Okay, awesome.
I'm like
just
very close to the end of this, but it started at the beginning of the slide deck. So let me just skip to the right slide. And
okay, no problem. I'll just it.
Yeah, here we are. Okay.
Awesome.
I guess I have to reshare one more time.
In the meantime, apologies, my Wi-Fi cut out in the beginning. There is an attendance form in the beginning. Okay. Yeah. So if you present
Okay. I don't know if anyone can hear me, but in case you can, I'm just going to finish. There's only like 2 slides left. There's more plots. At the end of the day, the takeaway is DORAM is ridiculously faster than what existed before and is still to this day by far the fastest. What does it mean in practice? Well, for the best binary search in literature, the best before us took n log n communication to do binary search. Now we're down to log n, just like a real binary search. Best heaps in literature took n squared log n communication. We're down to n log n. If you try to implement Argon 2, which is a password hashing, a memory hard password hashing algorithm, we just used back of the envelope calculations to come up with this. I didn't actually implement this, but using FlowRAM, the calculation says it would take approximately 20 petabytes of information of data transfer, which is a lot. Using DuoRAM, it would take about 1 terabyte, which is still a lot, but in comparison, a lot less. A lot less. Yeah, so the takeaways are impossibility results are but a challenge. Really, the right way to think about an impossibility result is telling you that you can't solve a specific problem in a specific way, not that you can't solve the problem at all. And that's exactly what we demonstrated here was you can't just naively try to attack this and expect to do something useful. You need to look at what is the impossibility result saying and figure out whether there's any workarounds you can use to actually do what you want to do without violating that result, which is precisely what happened here. Other takeaways are MPC is a thing. It's a really cool thing. It's actually a thing that you will probably all be using in the not too distant future because there are many big companies out there actively looking at use cases for this. ORAM is also a thing. It's also a really cool thing. Distributed ORAM is a thing, and it's a really cool thing. And it can be surprisingly efficient. So we can get round complexity that is constant, super small, online communication complexity that's constant and super small, and computation that's, never mind, let's not talk about the computation. Then that is the end of my presentation. So I don't know whether there's any good way for people to ask questions here or what, but if there is, I'm happy to take them. I don't know whether there is though. I guess I'll let Yasmin tell me.
Hello again. Yeah, I don't know if it was just me. You were a bit lagging. But I am interested. I must have missed it on my end. You talking a little bit about the impossibility result and maybe the applications. I know you kind of skimmed over the applications towards the end, but maybe explaining a little bit more.
Yeah, so I mean, the applications are basically anything that a computer can do, MPC can do. So we're looking right now. There's I actually am in the process of applying for some grant money because we want to go and do something with MPC. And the problem that we're looking to solve is there are a lot of mutually contradictory laws on the books right now if you're trying to do interprovincial or international commerce. Largely, these come from data protection laws. So like something like GDPR might say, in order to be in compliance with GDPR, if you have data about customers, that data must reside in the country those customers are about, and you can't just send it over borders into a data center in some other country. Some other country might say, in order to properly pay your taxes and not commit tax fraud, you need to compute this thing, which involves you doing a database join that involves taking databases about users in different countries and putting them together in one place, thus violating the data residency laws. And so then the companies are left with the decision of, do I violate GDPR or do I commit tax fraud? I have to pick one or the other. And so currently they violate GDPR. There's sort of a gentleman's agreement or understanding amongst regulators that if you literally can't comply with a law because it would be way too onerous or technologically infeasible, then you're not going to get punished for breaking that law. But as soon as it becomes easy and everybody else is complying, then suddenly your excuse for non-compliance goes away, and the penalties that exist in the books might actually be thrown at you. In the case of GDPR, this is, I don't remember for sure, it's something like 4% of gross revenues is the penalty that you can receive. So if you're like Google, that's like many billions of dollars. And Google is one of these companies that is making the choice of, do we violate GDPR or do we commit tax fraud? And they violate GDPR and they don't get fined because they have no choice. So what we're looking at is places where you can use multi-party computation to satisfy the data residency laws and other data protection laws, both in letter and in spirit, while not committing tax fraud. And so as part of this, I actually was trying to find industry partners, and I went to contact a friend of mine who I thought headed up the crypto team in the extreme computing group at Microsoft. So he's a very senior fella by the name of Brian Lamacchia. I went to contact him and realized, oh, he's not at Microsoft anymore. Where is he? It turns out he left Microsoft to go head up a nonprofit that is basically trying to evangelize for MPC because he thinks this is the future, and has left his like exec leadership role at Microsoft to try to like get companies using MPC. So I'm not the only one thinking this stuff is going to take over the world, but I also recently did consulting for the Bank of Canada, looking at whether you could build privacy-preserving central bank digital currencies based on multi-party computation, so that you could have like privacy similar to the most private of the privacy coins, but with anti-money laundering laws and anti-terrorist financing laws and all of the other stuff that governments want to be able to enforce, still enforced. But if I go and spend $5 at Tim Hortons, nobody knows that I went to Tim Hortons or how much I spent or anything. It just sort of magically works using MPC. So there's like the big things like that, and then there's more mundane things. There exist already some like smartphone apps. If you have your genome on your smartphone and someone else has their genome because you bought them from 23andMe or something, there are apps that actually, I can't say these are like real good apps, but there's proof of concept apps that you can use to have your phone connect to someone else's phone and figure out whether you are genetically compatible and are likely to have babies with birth defects based on your genomes, but you don't reveal your genomes to one another. You just figure out, is there any like troubling chromosomes in common or something like that? So there's applications like that and sort of everything in between. If you can do it on a computer, but it makes you feel a little bit creeped out knowing that if I do this, some random third party is going to learn this data about me. So, well, in principle, it's easy. In practice, I don't want to do that because I don't want to reveal this information. MPC is the solution, right? Because you can do it without revealing your data. Yeah. Does that answer your question?
Yeah, the application of MPC.
Right. Yeah. So the impossibility result basically.
This
is a. Oh, sorry. Go ahead.
Oh no, go ahead.
Okay. Yeah. So this is a basic thing from information theory. For those of you took 329 with me. Probably lots of people who would have been in the audience have taken 329 with me. We always cover one-time pad there. One of the first things you learn about crypto is one-time pad. And when you're learning about the one-time pad, you typically come across the claim that the pad has to be as long as the message or you don't have your perfect privacy. So this is a more general information theory thing that says if you have n bits of data and you want to encrypt it or perfectly hide it so that it's literally impossible to recover based on the ciphertext, not just computationally hard, but even to somebody with like infinite computing power, there's just no strategy that would possibly work. You need to have as many bits of randomness as you have information and use that to hide it. And if you have fewer bits of randomness than you have information, you can't perfectly hide the information with that randomness. And so when you translate that here, it basically says, if I want to multiply secrets, I want to give you my share, but not have you learn anything about my share because that would reveal something about the secret. I need to add at least as many random bits as there are in the share and then send that over to you. So if you have a vector with like n words worth of randomness or worth of secrets, then that naively seems to imply that I need to take n words of randomness and then add those to the n words of secret and then send that over. And basically what we observed was you don't have n words of secret. You had one new word of secret for each write. It's just that it's hidden within something of size n. And so you're not hiding n things, you're hiding one thing in a haystack of size n, which is different. And the impossibility result that says you can't use fewer than n words of randomness doesn't actually apply here.
Thank you.
Hopefully
I think we have
answers.
A comment. Let me just. Yes, that did answer it. Thank you.
Okay.
This is not really a question, but a comment.
Okay.
I don't know if do you have access to the comments? I can just show it.
I don't see anything except for maybe
Matthew says.
Oh, okay. Actually, I do see it now.
Now you should be able to see it.
This is so cool. Thanks for sharing this too. I got here. Oh, yeah, you're very welcome. Yeah. This is how research goes. You spend like a year thinking about something and doing nothing with it. In fact, in this case, I went from 2017 when I first had the idea until 2021 when I was like, hey, I think I'm gonna like really start thinking about this. And then in 2022, I was like, by golly, I know how to solve that problem. And then by 2023, it was published.
Yeah, no, I can only imagine the roller coaster of emotions to get to that conclusion. I personally don't have questions, but any more questions? You explained everything pretty well. Oh, we have another question here.
Yeah,
so Fam says, oh, you can read it.
Well, I don't have a great answer.
Is there...
I have my, so there's sort of a few answers to that. One answer is there are a few companies that are using it right now, but it is very early. So I mentioned using it to satisfy data protection laws. It actually has been used once that I'm aware of by the government of Estonia in order to do some computations that would have been illegal under European data protection laws. They actually got a court ruling that using MPC to answer those questions was not a problem. but doing it using traditional computing would be very illegal and not at all acceptable. So they were, I won't bore you with the details of what they were doing, but there's a paper called, what is it called now? Something in taxes. It was published in PETS 2016, I think. And they were trying to figure out whether like certain investments that they had made in IT education had paid off, but it turned out that the data they needed was distributed across multiple ministries, and it was illegal to combine it because data protection laws said you can't just do that. But the court said the question you're trying to ask does not have a sensitive answer. That's fine, but we don't know how you could get that answer without breaking the law. And then they said, oh, what about MPC? And the court said, yeah, that's cool. And then they did it. There are a handful of companies that I have consulted with over the past few years that are building relatively small scale prototypes of this sort of stuff. So there are some people doing it, and we're just very early. But it's also the fact that usually when you describe something like multi-party computation to lay people, they think you're a lunatic because it does stuff that is obviously impossible. So multi-party computation is obviously impossible. Zero knowledge proofs are obviously impossible. There's a handful of cryptographic primitives that when you first hear about them, they're doing something that is obviously impossible. And so when something is obviously impossible, you tend to not try to do it because you don't think you can. And so this is actually a different research grant that I recently submitted, was around trying to, better communicate that some of this stuff is not actually impossible, right? It may seem impossible, but it's because you're not looking at it the right way. You actually can do these things. So MPC is one of these things that it's slow and hard to use. That's part of it. But the bigger thing is that most people that would want to use it don't realize it exists and think that the problem it's trying to solve clearly doesn't have a solution. So they don't even go looking for solutions, because why would you look for a solution to a problem that you know has no solutions? You're wasting your time. Except in this case, it turns out, yeah, there's actually solutions, and there's a bunch of people doing active research on it. But we're currently at the place where, like, if you wanted to build a product with multi-party computation and you wanted to do it right, you'd have to go to one of the few hundred experts in the world who are actually competent at this and hire one of them to do it for you. You can't just find like off-the-shelf software that's any good. You can't find textbooks that will help you get good at it. Reading research papers is very difficult and like a full-time job to get up to speed with this. So we're in that area where even the people who do know that this is a thing, it's very hard for them to take advantage of it. But I would say 10 years from now, it'll be pretty widespread.
Just a follow-up question to that. You mentioned briefly your work with the Bank of Canada, and then now mentioned that the government of Estonia kind of tried to adopt this, used it in some way. Do you think other governments would likely try and do the same thing?
I do think so. Probably, like, I'm not sure whether any government will build a CBDC based on MPC. I don't even know, like, I mean, when you're working with the Bank of Canada, they're pretty hush-hush about what they're actually doing. So I knew what I was working on, but like I didn't know exactly how that fit into the grand scheme of things. I was doing what's called a proof of technology. So they just wanted to figure out, like, is this even remotely feasible? Because if it is, we'll consider it. And if it's not, then we don't have to consider it. I don't know how many other proofs of technology they may have had going on in parallel, looking at different kinds of technologies and so on. But if I had to guess, probably we're not going to see it in that context anytime in the near future. However, I do think that things like what the Estonia government did will become more and more commonplace. Canada's in the process of revamping our privacy laws and putting more strict penalties in place. California recently adopted a GDPR-like law. GDPR is, been around for a while, and other countries are starting to adopt this sort of stuff. So the requirement to actually do it this way is going up, and it's very hard for governments to ask companies to behave certain ways if they're not doing it themselves. So I suspect that we're going to see governments using this just for that reason, similar to how like the U.S. Census Bureau is one of the early adopters of differential privacy, and by far the largest scale differential privacy computations ever done are the U.S. Census Bureau. I imagine that we'll see similar trends like that where governments are early adopters because at present, the cost benefit analysis is a bit iffy for companies because the technology is still young. There's a lot of research left to be done. It's very costly to develop this stuff and then very costly to use it. Governments are more inclined to do things that are not profitable if it's societally beneficial, and then companies are going to follow suit as technology becomes more practical and easier to use without breaking the bank. So I do think we are going to see more governments using it. But the project that I have going on right now, we're really trying to basically, my goal at the end of the day is to make it so that companies can't just say, oh, we violate the data protection law because we have no choice. Because I want to give them the choice so that now it's, okay, well, if you decide not to use this technology, then you pay the massive fine. That's your choice, right? The choice isn't, do I break the data protection law or do I commit tax fraud? The choice is, do I get a massive fine for breaking the data protection law, or do I use multi-party computation to not break the data protection law? That's sort of my vision. So if I'm successful in like 5 years, everyone will be doing it, but that's a very ambitious goal, so who knows? That's a good question. So no, that's not really like, it depends. If you are a user who has outsourced your data to a multi-party computation protocol, you're absolutely right. There's no good way to figure out if the other part starts doing MPC. If you are actively participating in the MPC, then you don't actually need to trust anybody. The stuff that I described here is all what's called semi-honest. So as long as everyone's following the protocol, no privacy failures can happen. But in practice, you actually do more stuff on top of this that makes everybody follow the protocol. So if somebody tries to deviate from the protocol, they will be caught and they will be sort of like booted out of the computation before any bad outcomes happen from that. So it depends on your vantage point, but in many cases, at least, you don't actually need to trust anybody to use MPC and to believe the MPC. MPC is actually designed for scenarios where you don't trust the party that you're interacting with. So one place where MPC has been used a little bit and is a very promising area is actually things like distributed anomaly detection. So you have different companies that, like say different banks that want to figure out whether some sort of like subtle financial fraud is going on that involves transactions across multiple institutions. And so they're unwilling and potentially even unable to share transaction details with one another because of privacy laws. But the fact that they don't have a global view of all transactions might prevent them from spotting certain types of fraud going on that span institutions. So they can use multi-party computation to do this. And so in that case, they don't actually need to trust each other. The worst that a party could do in that case is not actually provide their own input to the computation, but then they have a vested interest in providing their own input, because if you don't provide your own input, then you can't possibly detect fraud that involves yourself. And like, what do you gain from this? So generally speaking, that's not the concern, but in certain scenarios, it could actually be a concern.
I think that might be it for all of our questions.
Okay.
If anyone has any last minute questions, please write it in the chat now. Otherwise, thank you again, Dr. Henry. I'm just gonna quickly put up the QR code because I couldn't do it in the beginning.
I guess that's why it was such an awkward start to the talk. I was like, am I live now? Okay.
Yes. Yeah. My Wi-Fi kind of failed on me for a moment, but it doesn't seem like we're getting any other questions in. So again, here's the QR code. I do acknowledge that there's a bit of a delay on the streams as well. So if you do have any other questions, put them in the chat, maybe email us, we'll relay it to you.
Yep.
And,
yeah, or
maybe
most of
give
you probably know my email. You can just email me questions and I will do my best to answer.
Yes. So thank you again. I will be ending the stream now.
Okay, thanks for having me.
For sure.